Welcome back to the deep dive. You sent over a stack of sources that really put us on the cutting edge.
They definitely do.
We're not talking about just optimizing things today. We're
Oh,
talking
yeah?
about this crucial moment where quantum computation and materials chemistry are colliding.
Right. It's where these incredibly hard problems, the ones that have stumped classical computers for decades, are finally starting to get solved. It's all about bridging those disciplines.
And the material is, well, it's pretty technical.
It is. It sits at a very high altitude intersection of computational physics, chemical theory, and, experimental quantum hardware. It's dense. But the story it tells is transformative.
Okay, so let's unpack this. Our mission for you, our listener, is to hunt for those key insights that prove this synergy is real. We're looking at three main fronts today, and they're all linked by this single theme: resilience.
That's a good way to put it.
First, we have algorithmic resilience, a new method called LAS for modeling materials that classical methods just, well, they break on. Then there's physical resilience, an actual experimental demo of true exponential quantum speedup on today's noisy machines.
It's a huge deal.
And finally, scaling resilience. So, new ways to handle large simulations like KQD and the creation of these next-gen electronic materials, electrides, that will give these quantum machines new problems to chew on.
The deep dive into synergy. Let's start with that first big roadblock. The classical inability to model certain complex materials. This is section 1, the quantum chemistry bridge.
Yeah, the sources jump right into this. This fundamental split in how we even model matter. When you look at a material, you have computational chemists and computational physicists.
Yeah.
And they see two completely different things, right?
They do, and it causes huge problems. I mean, think of it like looking at a dense forest. A computational chemist favors the real space molecular perspective. They see the individual trees.
So the local bonds, the molecular fragments.
Exactly, what's happening in that specific locality. But then the computational physicists, they favor the reciprocal space dispersive perspective. They see the extended canopy.
The global pattern.
The global pattern, the long-range periodicity of the solid. They're thinking in terms of continuous energy bands across the entire thing.
And while those two views work fine for the extremes, like simple molecules or perfect crystals, the real world is full of materials that fall right in the middle.
Precisely. You have things like metal-organic frameworks, MOFs, or organic semiconductors. They have characteristics of both. They demand an integrated approach, a bridge.
And that's where this proposed solution comes in, the Localized Active Space, or LAS, approach. This is the attempt to build that conceptual bridge.
It is. LAS takes the concept of an active space, which is a way to handle the most important correlation-heavy electrons in a molecule, and it extends it. So instead of one molecule, it applies it to multiple molecular fragments through a product form wave function.
So if we're modeling a crystal, LAS is treating each unit cell on its own, but it's keeping track of how they all interact.
That's the genius of it. And because it treats each fragment individually, it lets you rigorously define local quantum numbers on each unit cell.
Like local charge or local spin?
Local charge, local spin, local excitation number, all of it. This gives you a natural, mathematically solid basis for studying complex dynamic processes.
Like charge or energy just moving through the material. Now, does this make the simulation process faster, or is it just more accurate?
Ultimately, both. The efficiency comes from a very strategic combination. They paired the LAS state interaction, or LASI, with something called multiconfigurational paired density functional theory, or MC-PDFT.
Okay, that's a mouthful.
It is, but just forget the acronyms for a second. MC-PDFT is basically a method that cleans up the messy, raw quantum data. It makes it tractable. So this combination is an elegant way to compute material band structures, which is the key to everything, that inherently captures the complex multi-configurational character that standard methods just miss entirely.
And that combination is the secret weapon against what the papers call the infamous delocalization error. That sounds like a big classical raid block.
Oh, it absolutely is. Standard density functional theory, or DFT, is the workhorse of computational chemistry, but it has this problem. It tends to artificially smear out electrons that should be tightly localized.
Which leads to fundamental errors in prediction.
Yes, exactly. So let's look at their proof. They use a stretched hydrogen chain, which is sort of a classic test case.
Right, because we know what should happen there.
We do. At a specific bond length, that chain should behave as a Mott insulator. It should be insulating with a clear energy gap. But standard DFT approaches, like PBE and SCAN, they get fooled by that delocalization error. They predict the system is nearly gapeless.
A complete mischaracterization of the material.
Yeah.
And LAS.
LAS state interaction nailed it. It accurately reproduced the Mott insulator behavior, and this wasn't some minor correction. It was a qualitatively correct description where the most common classical methods completely failed. It just proved the algorithm's resilience.
And for a real-world complex material, they looked at bulk nickel oxide, NIO. That's a notoriously difficult one to model, right?
It's a benchmark. The goal is always the band gap, the energy needed to kick an electron into a conducting state. The experimental value for NIO is 4.3 eV. Getting close is tough.
And they got.
Using the refined method, LASTPBE0, they estimated a band gap of 4.30 eV.
Wow. That's incredible.
That level of agreement is exceptional. It shows this isn't just some theoretical curiosity. It's a serious tool for modeling really challenging three-dimensional solids.
A huge win for theory.
Okay.
The theory is great, but it only matters if the hardware can actually keep up. And that leads us right to the second challenge, physical resilience against noise and this demonstration of exponential speedup.
Right. We're now squarely in the NISQ era noisy intermediate scale quantum. The hardware is here, but it's full of error. So the challenge isn't just solving a problem, it's showing algorithmic quantum speedup.
A real scaling advantage that beats classical computers, even with all the noise. And to do this, the researchers turned to Simon's problem. For our listeners, Simon's problem is pretty simple in concept. You've got a black box function, and you need to find a secret pattern hidden inside it.
That's right. And it's so significant because it's the historical precursor to Shor's algorithm, the famous quantum algorithm for factoring large numbers.
Then the gap between classical and quantum on this in an ideal world is just massive.
It's exponential. Classically, solving it scales at O of 2 to the n over 2. That means adding just a few bits makes it impossibly long. A quantum computer, in theory, solves it linearly, O of n.
Linear time versus exponential time. Seconds versus years.
That's the difference we're talking about.
Yeah.
But, current quantum computers are so noisy, they couldn't just run the full unrestricted test. They had to limit it.
How do they do that?
They focused on a version based on the Hamming weight W-wood, which is just the number of ones in that hidden period. In this restricted version, the classical difficulty becomes polynomial, so it doesn't look quite as hopeless on a classical machine.
So why bother with the quantum computer then?
Because if the quantum solution still follows a polylogarithmic model, which scales even slower than any polynomial, you can still prove an exponential advantage. They ran these experiments with circuits up to 58 qubits on IBM's big superconducting processors, Sherbrooke and Brisbane.
And the result? Did they get that bona fide quantum advantage?
They did, yes. They showed that exponential quantum speedup held, extending the test up to a Hamming weight of 7. It's one of the clearest demonstrations of an algorithmic speedup for this kind of problem on real current-day hardware.
But here's the crucial takeaway, and it speaks right to our theme of resilience.
Yeah.
They only got that speed up because they were masters of noise management.
That is the punchline for the whole NISQ era. The raw hardware alone often fails. The speed up, the range of W values they could test, it was all significantly enhanced when they used sophisticated error controls.
The first one being dynamical decoupling, or DD.
Right. DD is about suppressing noise while the circuit is running. Think of it like constantly shouting at the qubits to keep them focused, to stop the environment from corrupting the calculation.
And the second was measurement error mitigation, or MEM.
And MEM happens at the end. Reading a qubit's final state is error-prone. MEM is a post-processing step to statistically clean up that final readout. The synergy between the two DD protecting the calculation, MEM cleaning the result, that's what let them actually see the exponential speedup.
The hardware is almost useless without that algorithmic resilience on top.
Almost, yeah.
Incredible. So we've tackled classical error with LAS and quantum noise with DDD and MEM. The final challenge is scaling. How do we take these complex simulations we talked about and run them on machines that are always going to be resource constrained? And that brings us to Krylov quantum diagonalization, KQD.
Exactly. With large Hamiltonians, classical computers hit a memory wall. Quantum computers, in theory, they eliminate that memory problem, but they run smack into the noise problem we just discussed. KQD is a technique designed to estimate the ground state energy of these big systems by sidestepping the noise.
How does it manage that sidestep?
It uses real-time evolutions to generate something called a unitary Krylov space. So it doesn't try to calculate the whole massive system at once. It projects the problem into this smaller, cleaner subspace. And the crucial finding was that the error from this projection converges exponentially quickly with the size of that Krylov dimension.
So you get clean results Fast.
Very fast. And that exponential convergence is what let them push the scale. Researchers use this to get convergence on the ground state energy for the Heisenberg model on up to 56 qubits. This let them explore a Hilbert space dimension of nearly 851,000 for just a 42-qubit problem.
A huge space, very efficiently. So why KQD over, say, the variational quantum eigensolver, VQE, which we hear about all the time?
VQE is popular, but it relies on time evolution spectra. And when you have to constrain your circuit depth, which you always do on noisy hardware, that spectrum can really diverge from the ideal solution. You get convergence problems. KQD avoids that. It extracts the energies directly from the projection of the Hamiltonian, so it's much more resilient to the short circuit depths we have to deal with.
So KQD is the new tool for conquering scale.
Okay, final piece of the puzzle. Materials breakthrough, the next-gen problems for these machines to solve. Tell us about surface immobilized electrides.
This is a breakthrough from scientists at Auburn University. And electrides are just a radical class of materials where electrons aren't bound to atoms. They literally float freely in open spaces within the material. The problem has always been stability.
They were unstable, hard to scale.
Very. And the breakthrough here is stabilization. They figured out how to attach these solvated electron precursors to robust, stable surfaces like diamond and silicon carbide. And this created surface immobilized electrides, which gives us this unprecedented precise control over free electrons. And that precise control leads to a dual application.
Right.
This is the aha moment of the research.
It really is. The tunability is phenomenal. Depending on how you arrange the molecules on the surface, those free electrons can do one of two completely different transformative things. In one arrangement, they cluster into isolated islands.
And these islands act like?
They behave like physical quantum bits, like qubits, ready for advanced computing.
So the material itself becomes the quantum hardware.
Exactly. But if you arrange the molecules differently, those same free electrons spread out and they form these wide metallic seas.
And these seas are useful for what?
They're incredibly reactive. They can drive complex chemical reactions. So you have a new generation of highly efficient low-energy catalysts for manufacturing.
That is a profound idea to end on. A single class of materials could be the engine for next-gen quantum computers and the catalysts that reduce the environmental footprint of heavy industry.
It connects everything we've talked about today. You have theoretical tools like LAS and KQD that let us model and scale these complex materials, and then you have the new material science, like these electrides, providing the next generation of physical systems for those quantum computers to solve.
The ultimate theme really is synergy. I mean, the exponential speedup from Simon's problem is amazing, but it's only realized when you pair it with sophisticated error suppression like DD and MEM.
And you'll need all of that resilience to simulate something as complex as these electrides. The future of quantum advantage depends entirely on this tight synergy. Algorithmic resilience, physical resilience, and materials innovation all working together. So I guess the question is, considering that new materials like these electrides promise to be both novel quantum bits and high-efficiency catalysts, how soon will the accelerating progress in quantum algorithms merge with these breakthroughs to fundamentally redefine both computation and manufacturing? That's something for you to explore on your own.
And that's the end of this deep dive. We'll see you next time.